Hey there, Mr. Sutton here, bringing you the BC Calculus 7.5 Part 1 homework solutions on alternating series error bound. On this problem, we have a function evaluated using this series and approximated using the first 78 terms of this series. Based off that, we want the error bound. So we'll notice that this series is alternating because of the -1 to the n here, and also because we're raising a number less than 1 to a variable exponent, this term is going to get smaller and smaller as that exponent increases. So in general, the terms of the series are alternating, and they are decreasing in absolute value to 0, which means that the error is going to be less than the absolute value of the next term. This is our alternating series error bound here that we met the conditions for. So the next term, since you used the first 78, would be the 79th term. So we can say error is going to be less than the absolute value of 0.1 to the 79, and we don't have to worry about the -1 because we're inside absolute value anyway. So you can turn this into 10 to the -79 if you want to, or just really leave it the way it is. Either way, you've got your error bound. For this problem, a function is evaluated using this series and approximated using the first 25 terms of it, so we want the error bound for that approximation. Okay, well, we have an alternating series, this -1 to the n power, and believe it or not, this is also one that decreases in absolute value to 0. The n squared is pretty impressive, but 2/3 to the n exponential growth here is going to outstrip the quadratic growth. So this actually gets smaller and smaller as you go further out for n values. So we have an alternating series decreasing in absolute value to 0. That means we can use the alternating series error bound, which says our error is going to be less than the absolute value of the next term. So we just have to figure out the next term, the value of that, and we've got our error value. Okay, well, we've used 25 terms already, so the next one in line is term 26. So that's going to be 26 squared times 2/3 to the 26 inside absolute value. And because we're inside absolute value, we don't worry about the negative here. So the error is going to be less than this. So let's actually calculate this on the calculator. So plugging in those numbers, we end up with about 0.0178 if we round to 4 decimals. But we want this we want an upper bound on the value. So we're going to make this 0.018 and put less than, just to be sure that we're giving them an upper bound out to 3 decimals. For this problem, we have a Taylor series for a function about 0 given by this series here. And we're told this converges to f for all real numbers. Fourth degree Taylor polynomial is used to approximate f of 1/2. We want the alternating series error bound. Okay, well, we better make sure that this actually meets the conditions of the error bound. I mean, we would hope it would if they're asking for it, right? But just to check, we see that we definitely have an alternating series here, -1 to some variable. And if we're plugging in 1/2, then we also have a series that is decreasing in absolute value to 0. 1/2 to some exponent, that's really 1/2 to the exponent. So we have a denominator that just keeps growing. So we can say that our terms alternate and decrease in absolute value to 0. So we actually can use the alternating series error bound. And that means that the error is going to be less than the absolute value of the very next term. Well, what's the very next term? Depends on the polynomial. In this case, they said we're using a 4th degree polynomial. So the next term is going to be whatever comes after the term that has x to the 4th in it. To figure out which term that is exactly, let's write out the first few terms of this series. So if we plug in 1 for n, this is going to be +1 over 3 factorial, and then we're going to have, let's see here, this is going to be x to the 2nd power, so x squared over 3 factorial. Next, plugging in 2, this is going to be -1 over, let's see here, this is going to be 5 factorial, x to the 4th. So that's our quadratic term, right, or our 4th power term right there. And then the next term is going to be the one we're going to use in our error bound. So plugging in an n value of 3, we've got +1 over 7 factorial and x to the 6th. So the value of the next term, the absolute value of the next term, is going to be the absolute value of 1/2 to the 6th power times 7 factorial. But if I'm writing 1/2 to the 6th, I can write 1/2 to the 6th, and 7 factorial is already in the denominator. Okay, Well, this was a no calculator problem, but fortunately, this is one of the answer choices. Choice C. On this problem, this series they're giving us, they tell us converges to S. Based on the alternating series error bound, we want the least number of terms in the series that have to be summed to get a partial sum that's within 0.03 of S. So basically, they want us to tell us the number of terms that's going to give us an error bound of 0.03. Since this is alternating series they're talking about, let's just verify the conditions before we do anything else. So we have alternating because of the -1 to the variable, and because the only thing really growing here is the denominator, we can also say that these terms decrease in absolute value to 0, in addition to alternating. So therefore, based on the alternating series error bound, that means our error is going to be less than the absolute value of the next term. Well, let's write an expression for the next term. So we can say that our error is going to be less than the absolute value of, I'm just going to call this 1 up top. The negative is not going to make a difference inside absolute value. So 1 over the square root of n plus 1. That's our next term no matter what n is. Now we want this error bound to be no greater than 0.03. So let me actually just set this expression equal to 0.03 and solve that on my calculator and see what n value gives me the exact error bound I want. To do this on the calculator, I'm going to put my error bound algebraic expression in y1, and in y2 I have the desired error bound. And what should my window be? Moving my calculator to get a look at my answer choices, because they didn't give me an interval, it looks like we're pretty far out here. We've got a range from basically like 0 to 10,000, I guess. So let me go to window, and let me do 0 to 10,000. It's not ideal, but hey, let's see what happens. So zoom fit, and very quickly our function bottoms out here because we've got this thing way zoomed out, and we've got the line 0.03 down here. We can't really see a whole lot on the grapher, but we don't need to because all we're going to do is figure out where these two things intersect. So let me do second trace. Come on. There we go. And intersect. First curve is one of these. Just press enter. Second curve is the 0.03. Press enter again. It'll figure it out. Our intersection, it's hard to see there, but it's 1110.11111. Okay, we'll take the calculator's word for it. So that's our magic n value. That isn't one of the answer choices, but I mean, why would it be? You can't have a fraction of a term index. So because the error bound is getting smaller and smaller as you increase the number of terms, that means to get the desired error bound here, we need to go to the next term in the series. So that would be term 1111. So that's going to be choice C. For this no calculator free response, we're given this function f of x equaling e to the negative x squared. And our first task is to write the first four non-zero terms in general term for f about x equals 0. So since this is about x equals 0, this is going to be a Maclaurin series, which means we can start with one of our predefined Maclaurin series, like e to the x, and just transform that to look like this. So e to the x, remember, was 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And let's do the general term too, x to the n over n factorial, just because we're going to need to transform all of these into something with this in it for this problem here. Okay, so now we need to turn this into e to the negative x squared. So to do that, I'm just going to substitute negative x squared for all the x's here. And I'm just going to simplify as I go. So I've got 1 still. This is now negative x squared. This is going to be positive x to the 4th over 2 factorial. And now for this one, we've got, let's see here, this is going to come out negative because I'm plugging in a negative. So this is going to be negative x to the 6th over 3 factorial. And that's the first four non-zero terms. The general term then, this is going to be, let's see, we're alternating, so we need a negative 1 to the n. We also need, this will actually be x to the 2n over n factorial. On this part, we want to use our answer from part A, which I will redisplay here, to find the limit as x approaches 0 of this monstrosity. Okay, well, this is another Maclaurin transformation problem. We just have more transformations to do now, starting with 1 minus x squared minus f of x. I mean, we've already got f of x, so we just have to subtract that from 1 minus x squared. Okay, what's that look like? Well, 1 minus 1 is going to be 0. Negative x squared minus another negative x squared is going to be 0. So really, we're just taking negative f of x from this third term onwards. So because these first two terms are canceling, we're just going to have negative x to the fourth over 2 factorial. And then negative negative gives us a plus x to the 6 over 3 factorial. And then I'm not really sure if I need to write any other terms. So for now, I'll just stick the general term in there. That's going to be, I'll call this just negative 1 to the n and all the rest of this stuff. Okay, so let's keep going. Now we need to divide by x to the fourth and take the limit as x approaches 0. I'm going to do both of those kind of in the same step, so I don't have to do a bunch of rewriting. So I'm going to write basically this expression equals the following. So I've got limit as x approaches 0 of, and now I'm going to divide what I just got on this last step by x to the fourth. So negative x to the fourth over 2 factorial divided by x to the fourth is just canceling the x to the fourths. So my first term inside my limit is just negative 1 over 2 factorial. For this next term, this is going to be x to the second over 3 factorial. And going onward, we end up with eventually x to the, let's see, this would be 2n minus 4 over n factorial. Okay, so now we need to take the limit as x approaches 0 of this craziness. Well, the key on this, as x approaches 0, I mean, we can always just try plugging in 0 and see what happens, right? If I just plug in 0 for x, and I really should be able to do this because this is a polynomial, so it is continuous. We've got, this is just going to zero out. This is also going to zero out. In fact, every term with an x in it is going to zero out. So we're really just going to be left with this negative 1 over 2 factorial, or just negative 1/2 term. So that's our limit of all this. For our next task here, we want the first 4 non-zero terms of the series for integral from 0 to x of e to the negative t squared dt about x equals 0. And then we'll do some other stuff, but let's do this part first. So note that we already figured out the original series that we're integrating in part A. So here is that again. We're getting a lot of use out of that part A. Hope you got that one right. And then we're just taking the integral of that from 0 to x. Now, just thinking ahead a little bit to see if I actually need to write out my evaluation box. When I take my antiderivative, this is going to be 1t, and the rest of these are going to have t's in the terms. So when I plug in this lower limit of 0, all of those are going to get zeroed out, and I'm just going to be left with the terms I get when I plug x in. So I'm not going to bother with my evaluation box. I'm just going to go straight to my antiderivative in terms of x. So then this is going to become, let's see, this is x is going to become a 1 minus, this will be x cubed over 3. Then we'll have x to the 5th over 5 times 2 factorial. And they wanted the first 4 non-zero terms, so let me go one more. So this is going to be minus x to the 7th over 7 times 3 factorial. They did not ask for the general term. I'm not going to give it to them. But I am going to move on to the next part of the problem, where we have to use the first 2 terms of what we just got to estimate integral from 0 to 1/2. Well, this tells you the integral from 0 to anything you want. So if you want integral from 0 to 1/2, you just need to plug 1/2 in for x in this expression we just wrote. And they said the first 2 terms. So we're really just doing 1/2 and then minus, this is going to be 1 over 2 cubed times 3. Note that I wrote approximately equals for this because I am doing an estimation. If I don't write approximately equals, I'm probably not getting the credit on this. Okay, so you can actually leave it like this because these are all constants. If you did want to simplify this, you've really got 1/2 minus 1 over 24. So this is going to be 12/24 minus 1/24, which is 11/24, but you didn't have to go that extra step. For the last part of this problem, they want us to explain why our estimate in part C differs from the actual value of this integral by less than 1/200th. So let's write out what that integral was in general in terms of x, because we're going to need that. So this is just my first part of part C that I wrote out before. And now one thing to notice here is that we have a series that is alternating. And is it decreasing in absolute value to 0? Well, it is if you plug in 1/2, because you're going to have 1 over 2. This is actually going to be 1 over 2 cubed, 1 over 2 to the 5th. So you're going to end up with all those exponential terms in the denominator, which is going to drag the value of this thing progressively closer to 0 as we keep increasing the exponent. So because we have terms alternating and decreasing in absolute value to 0, that means we can use our alternating series error bound, which says that our error, which is what this 1/200th is getting at, our error is just going to be less than the absolute value of the next term. Well, what's the next term going to be? We used the first two terms to approximate in part C. So the next term is this third term here, this x to the 5th over 5 times 2 factorial. The value of this term is just what we get when we plug in 1/2 for the x here. So that's going to be 1 over 2 or 2 to the 5th rather, times 5 times 2 factorial. All this craziness. Now this is a no calculator problem, so we're going to have to evaluate this far enough to see that it's less than 1 over 200. We want to be sure, right? So we've got, let's see here, this is really, I'll do the easy part first. 2 factorial is just 2. 5 times 2 is 10. 2 to the 5th is 32, so we really have 32 times 10. So this is 1 over 320. 1 over 320, since our denominator is larger than what we wanted here, this is definitely less than 1/200th. So we've shown exactly what they told us to.